We will now look at the optimal algorithm to replace pages. It's written as OPT algorithm, and this is assuming that we have perfect knowledge of all the page references. So we are going to look at the same page reference string that we used in the FIFO example, and we are going to assume that we have the complete knowledge of the sequence of page references, and we'll see what is the best we can do even with that perfect knowledge. And we are still going to aim for minimizing the page faults. We are going to replace the page that will not be used for the longest period of time in the future. So this requires future knowledge. So we need the knowledge of all the page references in the future, which we are not going to have. We can predict it, but we do not have that for certain. But we can develop an algorithm for comparison purposes, assuming that we do have that perfect knowledge. Just to quickly recap, FIFO, even though it was a very simple algorithm, easy to implement, the problem was it resulted in a lot of page faults. So we are trying to minimize the page faults in FIFO-based algorithm by using some aspects of the optimal algorithm. So let's see the optimal algorithm in action. We have the reference string, the page reference string as 7, 0, 1, 2, and so on. We have 20 page references in that particular sequence. At each reference, we are also showing the 3 frames present in the physical memory. So for example, when page 7 is referenced, we have a page fault and we bring in page 7 into an empty space, followed by another page fault due to request for page 0 and then page 1. But at the third location here, page 7, 0, and 1 occupy the 3 allocated frames. So when we request for page 2, we are going to have to throw one of these 3 out. So we are going to try to look in the future and see which one is going to be referenced very, very late. So 7, so let's see if 1, if we throw away 1, we are going to need it over here. 0, we are going to need it right here. So we should not be throwing 0. But if you look at 7, we will be needing 7 way late. So that means that I can replace 7 since it is not needed for the longest time. As you can see, 7 is needed way down the line right over here. However, 0 and 1 were being referenced earlier than 7. So that's what the optimal algorithm is based on. And we follow this approach throughout the 20 references. This will result in a much fewer page faults. So in this case, we went down from FIFO's 15 page faults to 9 page faults. So that's about 9 over 20 page faults. So that's the best we can do, even with the knowledge of future page references. That's the best we can do is 9 page faults. So why do we need this? Well, we can use this for an approximation, right? So we can develop algorithms which sort of borrow some things that work in the optimal algorithm, and we can certainly use the optimal algorithm as a benchmark for comparison. So we get a bound as to what is the best we can do in terms of page faults for a given page reference string. This, of course, is based on a prediction. So this algorithm cannot be really implemented fully, but we can certainly look at the behavior of programs and sort of predict some aspects of programs. So it can be approximated. All right, so this is it in terms of the discussion on the optimal page replacement algorithm.